Okay, let's check problem 2 here. Problem 2 is, there we go, it's the triple capacitor. Dun, 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 dun. So some weirdo has decided he wants to, not triple capacitor, but a triple plate capacitor. So he built a capacitor with 3 plates. I really should probably just draw lines for these, or I could even use a rectangle, whatever. Okay, so he does these things and he hooks wires up, and so he puts the one in the middle at a voltage V sub B, and the one on the outside at V sub A. That's the way I drew it. But what I'm going to do actually is I am going to say, and we can do this arbitrarily because we can reset zero potential anywhere. I'm going to say then that the 2 outside ones have a voltage of 0 volts, and the inner one has a voltage of V. And so what's going to happen? And V is going to be positive, so this is going to be plus V. I'm just going to say arbitrarily it's a positive voltage. Okay, now this triple plate capacitor has a thickness, a total thickness like this of little d, and the area of each plate is A. Okay, so what happens when you charge this thing up? First of all, the thing to understand is that in this capacitor you have to conserve the charge. Any charge you take off of one plate has to come back on another. That's true for all capacitors. So what you're going to have is you're going to have charge is going to accumulate on the positive voltage plate. Positive charge will accumulate there. So this plate will get a charge of plus Q, okay, and then the negative charge, or negative charge equal in magnitude to this, will be split between the other 2 plates. So it's going to be negative Q over 2, negative Q over 2. Okay, so we've got 3 plates now, and each one has a different charge on it. And so now we need to figure out what is the, how much charge can we accumulate at a given voltage. Okay, so what's going to be the capacitance. So let's remember here capacitance, and let me draw this over here. Capacitance is most often used in this equation. The charge on a capacitor is equal to the capacitance times the voltage difference applied to the capacitor. Okay, for our purposes we're going to find the capacitance by rearranging this. C equals Q over V. So we have to find what Q is and how that relates to V, okay, and then we can figure out what the capacitance of this thing is. Okay, now for a 2-plate capacitor, which is basically your standard model, okay, for a standard capacitor, the capacitance is equal to the plate area, so the area of each plate, times epsilon naught, which is the universal constant, equal to 8.85 times 10 to the minus 12, divided by the distance between the plates, d. Okay, that's for a standard 2-plate capacitor. Here we got something different because we've got 3 plates, and so we have, really what we have is these 2 plates are d over 2 apart, and then these plates are also d over 2 apart. It's evenly split. Okay, so let's see. What's going to happen here is you're going to have an electric field developing between the plates. Now the electric field here will point from the positive charge towards the negative charge. So in here the electric field will be like that, and here it will point from the positive charge toward the negative charge as well. Okay, so there we go. There is the direction of our electric field. What is our electric field? Well, there are 2 ways to find the electric field, and the good news is that we can do both ways and then set them equal, and that'll solve our problem. So one way is to look at voltage and distance. So the way of going from voltage to E field, okay, this is one way of doing it, is basically to use, we're going to use essentially this equation, VB minus VA equals negative electric field, that's an electric field vector there, dotted with delta R, which is a vector going from A to B. Okay, now what this, in practice, what we're doing here, the other sort of version of this is that the electric field in the y direction is negative delta V over delta y, and the electric field in the x direction is negative delta V over delta x. If you use 2 points with the same x coordinate for this one and 2 points for the same y coordinate for this one. So we've been over this in class. And if we take this one here, really, and apply it here, we can say, look, between this plate and this plate, if we go, so I'm going to take orange. What time is it? Oh, plenty of time. Okay. I'm going to take orange and go like that and say, this here is my delta y. So I'm going to say, for this delta y equals, and we're going up. So I'm just going to use the standard x and y axes like that, okay? So we're going up, so delta y is plus d over 2. And if we go from here to here, delta v is plus v, right? Because we go from 0 up to v, okay? So we're changing, do you think v minus 0, and that's our delta v, okay? So that means the electric field in here, in the y direction, and the electric field is only going to act in the y direction because we've got these plates lying along the x-axis, okay? So the EY, which is going to be our entire electric field, is negative delta V over delta Y, and that's going to be negative V over D divided by 2, which is then negative 2V over D, okay? So if you're with me so far, then we're doing pretty well. Can I move this crap? Sort of, a little bit. Okay. So I'll just have to fix stuff. Okay. So 2V over D. There we go. Okay. So that is our electric field in this area here. And then obviously our electric field up here will be symmetric. So the electric field, or when we go from voltage to electric field, so that's using this method here, okay, what we get is the electric field, the magnitude of the electric field is 2V over D, okay? No big deal. All right. Now, the other way to get it is to go from charge to field. So, charge density on a plate to E field, okay? That's going to be our method 2. Now, if we have one plate, just one plate, okay, one plate with charge on it, then the electric field generated by that charge near the plate, and we're talking about near the plate for all the things here, is going to be, let's see, it's going to be Q over 2 times the plate area, so 2 times A times epsilon naught. I hope this is not out of the boundary. I hope this is still visible, okay? So this is going to be the charge on the plate divided by 2 times the plate area and epsilon naught there, where epsilon naught, again, is the same universal constant, 8.85 times 10 to the minus 12. Okay? That's for one plate. Now, the tricky thing is when you have more than one plate. So one way to look at it, if we had just 2 plates, then we would simply take these two, or we would take the field from each plate, and if the plates had opposite charges, then these two fields would add up because they'd be pointing in the same direction between the plates, and we just have E equals Q over A epsilon naught for 2 plates. But we've got this 3-plate thing. So one way to look at it, I think probably the best way to look at it, is if you are, I'm going to say, let's see, I'm going to take my red marker and mark in here, okay? So I'm going to say if we're in this spot, okay, at the X that I just marked, X marks the spot, what's going to happen is the top plate, so I'm going to call this one, let's see, I'm going to call this plate 1, plate 2, and plate 3, okay? So the electric field from plate 1 will be pointing upwards because it's a negative charge, and it's got a Q over 2 charge. This formula is for a Q charge. So the electric field from 1 will be Q over 4A epsilon naught. Okay. I hope I don't run out of space here. Okay. The other thing, the next bit is, let's see, let me do that, And we'll take, yes, I know, you love watching me fiddle with stuff. Okay, so I'm going to take that, and that's our 2-plate capacitor. Okay, and then I can move this guy up a little bit, sort of. Okay, and then, help, there we go. Okay, so that works well, and then I just, no. Okay, whatever, screw it. Okay, so that is my, there's got to be some way to, okay, screw it, fine. Okay, so that is our electric field due to this guy. Now, this guy here is going to have an electric field in this area pointing downward, okay, because that's towards number 3. So I'm talking about the electric field from 3. So electric field from 3 will be the same as this because 3 has the same charge, right? And the electric field for a flat plate doesn't attenuate until you get pretty far from the plate, okay? So this will be negative Q over 4A epsilon naught, and I am going to have to just beg a tiny bit of space here. Okay, so in this area in here at the X, E1 plus E3 cancel, right? And so all that's left is E2. And E2 will be then, it'll be upward, and it'll be Q over 2A epsilon naught. It'll just be this, okay? And this, in fact, will be our total electric field because E1 and E3, see, are going to cancel. One's going up and one's going down. Only in between the plates 1 and 3, only 2's field doesn't get canceled, okay? So this means the plate from 2 in here will be Q over 2A epsilon naught, and that'll be the entire field. And so now we can then take this and say, okay, fine. The answer here is E equals Q over 2A epsilon naught, and that's the magnitude of the field inside this triple plate capacitor. And now you set these two equal, okay? Finally, we are, getting to the whole point of this thing. We take these two guys and plug in here, and you say these are both equal to, actually I'm just going to come around here and say 2V over D equals electric field, which equals Q over 2A epsilon naught. And we rearrange those, and again, a little more space. Ooh, okay, that's plenty. Okay, the capacitance, which is Q over V, then becomes, so what's the best way to arrange this? So let's bring the, let's say we brought the V under here, and then we would get 4A epsilon naught over D is the capacitance of our triple plate capacitor, which is, you will notice, let's see, this was the capacitance, this here was the capacitance of a parallel plate capacitor, your standard 2-plate model. This is the capacitance of the wacky 4-plate, sorry, not 4-plate, 3-plate version, and it's 4 times as much. So this is actually, if you're trying to fill up, if you're just trying to fill up some space, this is a certain amount of space, this is a better capacitor design. The problem is it's harder to make it like this, and what the limiting factor really is how close you can get these plates. And it turns out actually there's no, you might as well make this into 2 different normal parallel plate capacitors. Let me show you another trick for analyzing this that one of my students came up with, and it's rather clever. But if you take this thing, and so I'm just going to cut and paste this section here, and just come down here and redo that. Okay, so that's good. Okay, so I'll keep the old result there. Okay, so what one of my students said is, look, this is really like 2 different or 2 adjacent single plate capacitors, or not single plate, sorry, standard parallel plate capacitors. So 2 adjacent ordinary capacitors. So you've got 2 capacitors here. Each of these capacitors has a capacitance of D over 2, or sorry, not a capacitance, each has a thickness of D over 2, okay? As it happens now, these guys in the middle are both at V, these guys on the outside are both 0. So what you're doing is you're taking this plate here and treating it as 2 different plates. And then this is a capacitor that gets negative Q over 2, and this one has Q over 2, this one has Q over 2, and this one has negative Q over 2. And what you get is then you've got each of these has a capacitance